Okay, here we are. This is video 9 from Calc 3. Should be watched on the 16th. And today we're starting functions. This will have a very different flavor from the last two chapters. Significantly different, but still linked. So and in some senses it might be a little easier because it's a little more comfortable. Okay. So first we're going to recall something from Calc 1, because I'm going to tie Calc 1 and Calc 2 to Calc 3. So in Calc 1 we talked at length about functions. Functions y equal f of x. And these are functions of a single variable, right, where x is our independent variable, or input, as engineers like to say. Okay? And so the domain of f is equal to, right? It's all the values of x that define, so they're all the values of x such that f of x is defined. Right? So wherever the input is defined as being put in and defining a function that way, that's our domain. And so and the range are just outputs. So the range is the outputs. All the y's we get, or all the f of x's we get, and then we graph them. We graph them as y's on the y-axis. So here we go. Right, here's the x-axis. Here's the y-axis, and all the domain points lie on the real number line, really. So there's x1, and maybe somewhere up here is f of x1, right? And this is the point x comma x1 comma f of x1. So yeah, input, output, and this thing makes a curve, right? A curve. Y equals f of x. Okay. Okay, so just so we have an example, an actual example to look at, let's let f of x be the function square root of 1 minus x squared. Okay. So the domain is going to be all x such that 1 minus x squared is greater than or equal to 0. Okay, and that happens to be from -1 to 1. Okay, and in this case the range, just from graphing it, is 0 to 1. Okay, so if we go down here and actually graph this thing, it's a little half circle here. And that's a 1 and that's a -1 there. This pen gives no resistance, so it's hard to keep it straight. Okay, and remember the domain again it's just numbers on a number line. All right. Now let's go to Calc 3. So we want to consider functions of the form f of xy, where the ordered pairs xy are the inputs. So we have two independent variables. Okay? And so the domain of f is some R. It's going to be the set of ordered pairs such that f of xy is defined. All right, so it's all the ordered pairs that are legal to input to f of x comma y. Okay, and then the range is what? It's z equals, it's all the outputs. Okay. So note that R, this region R, is a subset of R2, right? So if we if we put some nice pretty axes here and called this X and called that Y, then this R could be my domain. All this space here, right? And one of the points in here in the domain could be x1 comma y1, right? So now the domain is ordered pairs. Okay, so any point on the any point inside R is called an interior point. And points on the edge are boundary points. Right, so boundary points and interior points. So this x1, y1, the way I have it drawn inside here is an interior point. And if I put another point over here right on the edge, called it x2, y2, this would be a boundary point. Okay. All right, so now we've defined what the domain is, and we're gonna look at a pretty cool example here. Okay. So example. Consider the function f of xy equals the square root of x squared plus y squared minus 4. And we want to find the domain and graph this thing, right? Okay, so the domain, I'm going to call it R again. It's all ordered pairs such that x squared plus y squared minus 4 is greater than or equal to 0, because you can't take the square root of a negative number. And so this is all ordered pairs x, y such that x squared plus y squared is greater than or equal to 4. Okay, well, x squared plus y squared equaling 4 is a circle of radius 2 centered at the origin. Right, so. And we want all the points that are outside of that circle because it's greater than or equal to, so I'm going to get some color here. So our domain is going to be all of these points. Right? This is actually the complement of the circle. It's everything outside of the circle, including the circle itself. So we do have a boundary here along the circle. Okay. If the function we had looked at was, we're not going to do this, but if the function we had looked at is 1 over this whole thing, then our domain would be x squared plus y squared minus 4 strictly greater than 0. That would be a greater than 0. And then we'd have x squared plus y squared greater than 4. And so we wouldn't include the boundary. And when that's the case, you make a dashed line for the boundary, and then it's everything outside of there. But that's not what we're doing. I just wanted to point that out. Take these out of here. Okay. So we're graphing this guy. Go away, eraser. There. Okay. Okay, so here I can put this right here. I'm just going to fiddle with this for a second, just to get a handle on. So apparently, if you put in the unit circle, all the inputs are going to be outside of here. So maybe I'll pick the point over here, 3, 3, and when I hit that thing with F, it's going to give me some point up here, 3, 3, F of 3, 3. And anywhere on this domain, I'm going to have outputs. But these pictures are already getting really sloppy, so let's use some technology here, because I think that's the right thing to do. And I've tried this a bunch of times, so I'm going to do my best to get this to work. I'm going to pull up GeoGebra, but you have to hold this down, and it gives you a split screen. Okay, and so this is the curve right here. Oh, I can't really. Can I write in this? Yeah. So there's the curve. It's actually a surface, not a curve. And remember that when we're graphing these, we're not graphing volume. We're just graphing a surface, so it's really the shell of this thing. All right. So now if you look at it, you can see that none of the points inside the circle give us any outputs. But everything outside of it does. So in particular, stop right here. If you see the point on there, I can't point to it with this pointer because it's in the app. Here, let me do this. So if I drag this over, that guy goes away. You go away. And then here, I'm going to, because I did. So here's a picture that I took, a screenshot of that function, and I should be able to write on it. Here we go. Okay, so this point here, which I just filled in as yellow, is an output. It's actually the output of the point 3, 3. And so this is 3, 3, F of 3, 3. Okay, this point here. And sure enough, if you take any of these other domain points here, they're gonna map to some point on the curve, like this, right? Anywhere, as long as I'm outside of the circle of radius 2, I'll be inside the domain and I'll get outputs. And that's pretty cool. All right. So if we carry on here. So now we've graphed our first function, and sometimes you do have to do a little sketch yourself, but to really get a handle on these things, let's get comfortable with this program. It's so simple and makes life a lot easier. Because if I sat here for 10 minutes and tried to draw this picture, I could never get it to look that good. Okay. So now we have functions defined. Functions in 3 space. Are defined. We just change the inputs. Instead of having 1 input, we have 2. And you can even go into 3 and 4. You just can't make pictures. Because now you're talking about 4th dimension, and we don't quite understand that yet. All right, so now that we have functions, let's talk about calculus, right? So first we talk about derivatives, right? Just like Calc 1, you start with the derivative, then you go to the antiderivative, then you go to series. Luckily, we won't have any series this semester. Well, luckily for you. Okay, let's talk about the derivative. We'll go back again. Let's consider the function f of x equals x squared plus 1. This seems to be my sort of go-to function whenever I'm talking about Calc 1. Get some better axes than the ones I've been making. and go away. There you go. There's x, there's y, and here's this little parabola, f of x equals x squared plus 1. So we talk about the derivative at length, and we go, okay, what's dy dx? Well, we know how to do that. It's 2x, right? And this says that if I take a little piece anywhere along this curve here, and I look at the slope of the tangent line, it's going to be rise over run, or dy dx, right? And so this is really clear. There's only two directions you go in. You go horizontally and vertically, dx dy, okay? And then we talk about the derivative. And let's evaluate this at 1. So we have 2. So this is the slope of tangent line at what's the point? 1, 1, 1, 2, 1, comma 2, right? And if I put that over here, get some color. If I graph this line, I get a tangent line, I'll call it L. Remember, L is unique. There's one and only one tangent line to a point in a curve in R2. So in R2, every point on a smooth curve has exactly one tangent line. And the slope of that line is defined by the derivative, right, dy dx. Okay. So let's jump to Calc 3. And look at, go away, and look at, come on. And look at f of xy equals this function we've been working with, x squared plus y squared minus 4. If I say take the derivative, it makes no sense. And here's really why. Here's the short answer with a long explanation. So I'm gonna get another copy of this picture. Right? Come on, you. Did this last time. Here. You have to tap it and center it? I'm not understanding this. Okay. All right, here we are. We're going to come back to this point that we've been looking at. Let's say I want to graph the tangent line at that point. Well, that was convenient. So there's a tangent line. There's another tangent line. There's another one. And another. Why doesn't it go on there? Right? So the point I'm trying to make here is that there are infinitely many tangent lines. To a point on a surface. And what we'll learn, not today or not even tomorrow, is that all of these lines lie on a single plane, and that plane is unique. But that's not really what's important there. What's important right now is if I ask you to, quote unquote, find the equation of the tangent line, it's nonsense because there's infinitely many, and that means it's hard to interpret the derivative. Okay? And so we have to talk about derivatives. So to talk about derivatives, derivatives differently. Right? It's not the same definition at all. It's close, but not the same. Okay, so talk about derivatives differently. All right. Well, I couldn't find a good picture, so I'm going to draw one, and then hopefully find a picture I can write on that's got this really well laid out. So this I actually feel it would be easier to do on a whiteboard, but I'm gonna give it a go because this is all new for everyone. All right, so I'm going to make my vertical axis like that. A horizontal one like that. And my y-axis like that. And let's see. Can I make this go away? Oh, I don't want the whole thing to go away. Darn it. Okay. It's all right. Like that. All right, that's better. And so we have z. Z, X, and Y. Okay, so up here, so we've already graphed this. We're going to take a piece of our surface, and this is my surface here. So this is just a chunk of the surface f of x equals xy, okay? And then somewhere down here is the point x naught, y naught. Let me clean that up. So somewhere down here is the point x naught, y naught, okay? And, sure if this helps. Yeah, it's going to help. If I locate the point on here, which is, I'll call it point P, and it has coordinates x naught, y naught, z naught, okay? So that's the point there. Okay, what I want to do here is fix. Fix the plane y equals y naught, right? So along here, I'm fixing this plane here, and it doesn't actually look that bad. Wow, maybe I could use some color here, green. Okay, and actually along here it should be solid because we're actually on the curve. So this heavy green line is where the plane y equals y naught, which is fixed, right? And here's the point, y naught. We intersect that, and then we think, all right, with this, fuck. This is going to do my head in. with this thing being fixed, so now we're saying we're only looking in one direction. If we let this thing be fixed and we just move in the x direction, so we're only moving in this direction, and we think of a line, so now we've got a tangent line, one of them, a distinct tangent line in this direction only. So of all the infinite lines that intersect this surface at this point, we're picking one, and we're picking the one that's parallel to y equals y naught at this point. So we're just looking at that. So what we do is we take the derivative with respect to x. Okay? But this isn't this is the partial derivative. This is the partial derivative with respect to x. So under this fixing here, we fix this y equals y naught at the point that we're given, and we can talk about. I like to think about this as being in the x direction, right? Because we're differentiating along this line in this direction, in the x direction, right? And there's no sidewards movement by y, okay? And so this derivative is the partial derivative with respect to x, and it's written as d crazy f dx, okay? And this turns out to be the limit as h approaches 0 of f of x naught plus h y naught minus f of x naught y naught over h, because the y's are fixed. So the only thing moving here is x. And so we have our first partial derivative. And it's actually a pretty good picture there. And with this, we can find the equation of the tangent line at this point. But I'm not going to do that because I just want to talk about the derivative. So, and we can also do this. Also do the same construction. Fixing x equals x naught. So now if I fix this guy and we run the same argument, only now we're going to go this way, and this whole picture is going to turn 90 degrees. We can define the partial derivative with respect to y. And we rate that d parse dy, df dy. And this becomes the limit as h approaches 0 of f of x naught y naught plus h minus f of x naught y naught all over h. Okay. All right, I'm going to stop here and pick this up on the next video.